All right. Let us build off what we ended with last time. So in the previous video, the last kind of half hour or so, talked a little bit about conductors and the electric field just outside the surface of a conductor, and we used Gauss's law to connect potentials and charge and on in electric fields on conductors. I will assume you have watched that because we will need that, but we won't need that for a little bit. We're going to now talk about a new topic called capacitance, or the actual objects called capacitors. And these are devices which are intended to store charge and energy. So these are devices intended to store and discharge energy. And charge as well, but the charge is kind of the energy carriers. So you might think, oh, so they're batteries. Well, not quite. A battery, we'll start talking about next time, is kind of, its intention is to kind of establish a potential difference and kind of drive current. A capacitor, kind of its primary goal is to store energy and then discharge that energy, which it may need to at a very quick or very fast rate. Batteries can kind of drive charge and push and move energy along. But since their intention is mostly to hold a potential difference across the two terminals of the battery, some sort of delta V, which can then ultimately drive current through a circuit, the energy that it can deliver, it does so at more of a modest rate. And if you need to discharge energy fast, the battery is not going to do it. You need something like a capacitor, which can be fine-tuned to discharge energy at whatever rate you need it to. So, for example, this is an antiquated example. Well, no, because smartphones still have flashes on their cameras. But when you discharge a flash and take a picture and your flash goes off, that energy is being stored. The energy to drive the flash, which you need a lot of energy in a very short amount of time, is being stored up in a capacitor near the bulb. And then when the flash is triggered to go off, that energy is quickly dissipated into the bulb. The flash goes off very quickly, and then the capacitor charges back up for the next time you take a picture. You could really kind of hear this happening on those old school disposable cameras that you could buy at like CVS or something like that. That whenever you took a picture and the flash went off, you could actually hear the capacitor kind of charging back up. You would hear a little whirling sound inside the device as it kind of like ramped back up. And when the flash went off, you would hear it, kind of you would hear it, the capacitor charge back up. So, and these things are in all your electronic devices. All these little things I have circled on the chip on the left, those are all examples of capacitors. And they come in various shapes and sizes and can be tuned to store as much energy or discharge energy at whatever rate you need it to. The very common ones, kind of the most common capacitors, are essentially two aluminum foil sheets that usually have like a piece of paper or some material in between the two sheets. So we've been spending a lot of time talking about kind of plates and the electric field between two plates. This is one of the reasons why, because the most common kind of capacitor is essentially two plates separated from one another. So, the goal for this lecture today is to just talk about some of the basic ideas of capacitance and capacitors, which again, the goal here, I know I already wrote this, but I'll write it again. Capacitors store and discharge energy. And I'll elaborate on that. Store and discharge energy, how? How is that energy being stored? In a battery, it's essentially chemical potential energy that is stored. That is where all that energy is stored. In a capacitor, this is all being done with electric fields. The capacitor store and discharge energy via electric fields. So essentially, You can think about this, and this makes sense. Actually, I'll do a little example that kind of motivates this as well. To create an electric field, right? Electric fields don't just come out of nowhere. Some sort of effort or work has to occur when you create an electric field. And so you can imagine, getting that work back somehow by discharging. So, to create the capacitor or charge the capacitor up, so essentially work will be done to create an electric field, and then allowing the electric field to kind of dissipate and go away will be the act of discharging the capacitor. So a capacitor is kind of generally defined. I said the most common was essentially two plates, but essentially if I have two conductors near one another, that can be used to create a capacitor. So I'm going to have two conductors. Two conductors create a capacitor. So here's the idea. Imagine you have two capacitors that are initially have no excess charge. So initially, both capacitors are neutral. And there's a small little demon who, what they do is they go to one of the conductors and they steal or they nab electrons, and they take electrons off one of the conductors and transport it and deposit them on the other conductor. So again, imagine a demon that steals electrons from one conductor and deposits them on the other. As it does this, and it just starts moving electrons along, there's going to be a net charge that builds up on both conductors. As it robs electrons from the left conductor, eventually there's a positive Q excess charge that forms on the left, and as it drops the electrons off, there's a negative Q excess charge that builds up on the right. So in this case then, a net charge develops on each, and therefore an electric field is created. And I can say something about where this electric field is. We talked about in the last lecture that the electric field inside the conductor is zero. The excess charges will rearrange themselves to some sort of equilibrium position such that there is no net electric field inside the conductor. All the charge resides on the surface of the conductors, and then immediately off the surface of the conductors, the electric field is equal to the charge density divided by epsilon. And then far away from the surface, the electric field gets established, and it might look something like this. There might be some electric field that kind of goes from one conducting plate or one conducting blob to the other. It might look something like that. Might be some electric field lines that go off in that direction too. There's some electric field that points from the positive to the negative. Like some sort of dipole-ish thing. So that's the electric field that gets established. I would make this blue. The electric field is created. An electric field, E, is created outside the conductors. Again, not inside the conductors, but outside the conductors. That also establishes a potential difference across the conductors. So it also establishes a delta V across the conductors. Where we have again talked about potential being as a scalar field that represents the agent, in this case the electric field, that then if there were charges in between the conductors, we could then be the potential difference would tell us something about how those charges might move. But again, all the information about the electric field is encapsulated in the scalar field V. And so there's a potential difference across the conductors, and again, we're building our kind of conceptual ideas of potential, right, where it goes from high, V goes from high potential to low, or the electric field points from high potential to low potential. So we can think of it as the positive conductor has a higher potential than the negative conductor. And again, I've screamed and waved my hands violently, saying that it's only delta V that has any physical meaning, and we've written down this connection I just talked about, that there is a connection between the potential difference and the electric field between 2 points. And so this delta V, the general definition, remember, was negative the integral of the dot product of the electric field dotted with dr, some path that you take from some starting point to some end point. And I've also complained that I find it kind of sloppy that sometimes the delta is dropped, and we'll just talk about the voltage of an object, or the voltage, but really when they write voltage, right, they mean a potential difference, or a delta V. Forgive me, I'm going to cave in, so to match the notation of your book and the problems we'll do. And let us define the voltage, which again is the potential difference across the conductors, across the 2 conductors, that form this general thing I'm calling a capacitor, as VC, as V sub C, as V sub C. And the way you can think of this to kind of reconcile it with the fact that I'm saying only delta V's really matter, let's call the potential, right, I'm allowed to create a reference point, someplace where I will say V equals 0. So you can think of this as, let me say that the negative charge conductor has a voltage value of 0, or potential value of 0. Then the positive conductor, which has a higher potential, has a value V sub C. So then V sub C can be defined as, it's the potential difference across the 2 conductors, or across this capacitor. It is, we will take this to be a positive number. So you can think of it as the voltage of the positive conductor relative to the negative conductor. So we could define this as negative the integral of E dot dr, starting at the negative and going out to the positive conductor. So again, what this is saying is, let's start at the negative conductor and end at the positive conductor through some path. So again, this V sub C, the drawing's a little busy, let me recopy. So let's see, if we call this plus Q and this is negative Q, and there's some electric field, that's kind of in between them. I could then take I could start somewhere in the negative conductor, so maybe I start here, and I take some sort of walking path that gets me to the end conductor, or the positive conductor at the end. So each of these little dashed lines is a little dr. And if I integrate, over this integral, that then gives me the potential difference, right? That was the definition we had for potential difference. We're going to call that the voltage of the capacitor, or V sub C. So, so essentially, so far, this is just definition. Now let's use this to, so again, when I write V sub C, think potential difference. But really, it's the voltage difference across the capacitor. Now, what else do we know? We also know that, if I think of the electric field that's been created in between these two conductors, that electric field was created because of an excess charge, or a net charge. When there was no net charge on each conductor, there was no electric field in between them. But as that demon moved electrons around, that established a net charge on both conductors, which then created this electric field. The strength of that electric field, it makes sense to argue, the strength of that electric field must be proportional to the excess charge. So I think we can all kind of buy that the electric field is proportional to the charge. Think of a point particle. It's some constant times q divided by r squared. For a point particle, it makes sense that for more general charge distributions, that the electric field should be proportional to the excess charge in some way. Therefore, it then makes sense to say that this integral should be proportional to the excess charge. Whatever that integral evaluates to, it should be proportional to the excess charge that's been established on the two conductors. Since that integral, with a negative sign, is then proportional to the potential difference across the two conductors, or the potential difference of the capacitor, together this implies that the voltage of the capacitor, which is equal to that integral, which is proportional to Q, so then this voltage is proportional to Q. So that there is a relationship, a proportionality between the potential difference that's created between the two conductors and how much charge the demon has moved over. When something is proportional to something else, that means they're related by some constant. So what this implies then is that Q is equal to some constant times the voltage. That's what it just means to be proportional. We call this constant of proportionality the capacitance. Capacitance. Again, it is a proportionality constant that connects the delta V you've created, or what we're calling V sub C, with how much charge was moved between the two conductors that make up this thing called the capacitor. And we will see that the capacitance depends only on kind of geometry and properties of the material, right? It has nothing really to do, right? It's a constant that will only depend on, say, how far apart the two conductors are, or the size of the conductors. Because you could think that it makes sense that the geometry should be involved somehow in terms of the kind of electric field that's established and the potential difference across the two capacitors. If it's, say, two lightning rods versus two long infinite sheets that has the same excess charge, either on two rods or on two sheets. So we call this the capacitance. And essentially this will be a constant that allows us to say something about how much energy can ultimately be stored in this capacitor. Now, there's an unfortunate thing that is happening here, and that we are running out of letters. And now we have the letter C and the letter V both corresponding to multiple things. So I'll just have a quick be careful aside, where if I want to ask what is the unit of capacitance, well, based on that equation, it looks like it's the unit of charge, or Q, divided by the unit of potential difference, which is then just coulombs per volts. But then notice here I have two different things that use the letter C, and then two different things that have the letter V, where this C is a symbol for capacitance, but then this C is the unit coulomb, which is about charge, and then this symbol here is talking about potential, but then this symbol here is the unit for potential, which is volts. Kind of unfortunate. We're simply just running out of letters. So all this is to say is just be careful when you're looking at these symbols, right? Know what's a symbol versus what's a unit. That's again why I continue to emphasize plug in numbers at the very end. Work in symbols entirely, and then when you finally have to plug in numbers, as long as you're using the SI units, you know that all the units will work out. We could help ourselves a little bit in that the unit of capacitance, and again I'll try and will be ultimately unsuccessful at remembering, and when I'm doing capacitance I'll put a little kind of tick or a serif, I guess this would be, on the C. The unit of capacitance, which we just said is coulombs per volts, we give it its own unit and we call that a farad, F. So the unit that is associated with capacitance is the farad. And let's see, in the pictures up here, you might be able to see that written on some of them. Like right there, we have kind of, this one is 2.5 microfarads, plus or minus 5%. Here's 400 microfarads. Some of these give kind of an energy and a voltage, which we'll get to how energy comes into this in a second. Let's see, any more farads? Here we got 0.022 microfarads. That's kind of all I can see right here. Yeah, anyway. So, and as you can see, kind of microfarads, plus or minus an order of magnitude seems to be kind of common in engineering and electronics. Now, let's actually get to the idea of energy being stored in a capacitor. So let me redraw my capacitor. So I have some conductor that is charged Q, some other conductor that is charged negative Q, that establishes an electric field, which I'll draw kind of is in this direction, which will be important. Right? We know it points from high to low potential. All right, we also know that the delta V, or V capacitance, which is the delta V from going from the kind of high potential side, the left side, minus the low potential side, is some positive number, some number of volts. And there's a relationship now between this kind of excess charge Q, this voltage, just potential difference, and this new thing we've defined to be the capacitance. Now let's go back to our demon. Our demon again, with his bag where he's stealing electrons. and moving them over. How much work does the demon have to do every time it moves a little bit of charge? You can imagine at first he probably doesn't have to do that much work. He takes an electron, there's no excess charge really anywhere, no electric field he has to work against, he can deposit that electron easily. As he moves more and more electrons, there's an electric field that's getting established that's pointing to the right. Where if I were to drop the electric field, if I were to drop the electron in that field, we would know it would want to move back to the left. It wants to go where the positive charges are and reunite. So the demon is doing work. It has to exert some effort. It doesn't just get to do this for free, like how carrying a ball up a hill. You have to do work to carry that ball up the hill, versus you don't have to do anything to let the ball go and it rolls down the hill. So the demon is exerting some effort, doing some work, in order to establish this charge excess. And it's also, in a sense, exerting some effort, doing some work to build up this electric field that's being created. And then every time it tries to move more charge over, it has to work against that electric field that's created in order to, build up Q and minus Q more and more and more. So how much work does the demon have to do? Is the question we're now going to ask. To essentially start from no excess charge and build up a potential difference of V. Which again, remember, that's what relates to the electric field. The electric field is encoded in the potential difference V. So how much work does the demon do to establish VC? This potential difference between the two. And we're going to define the energy, the potential energy, to be 0 in V. So we're going to define or take V to be 0, or similarly the potential energy to be 0 when there is no excess charge. So, how do we figure this out? Because again, you can think of it that the demon is creating a potential energy that if all those electrons were suddenly released from the conductor, they would all whiz back to the positive charges, like how the ball would then, if let go, would fall down the hill. There, the potential energy would be cashed out and turned back into motion. But in order to get all those balls at the top of the hill for us to let go, someone or something had to carry them up. Similarly, this demon is carrying all those charges over, establishing some potential energy, some energy that's locked in this capacitor, that then, when some mechanism allows charge to flow again, can be released. So, here's the idea. And we can do this in the calculus limit. Right, so the demon moves some small amount of negative charge, right? I was using the examples of electrons, but we're going to say it moves some small amount of charge, of negative charge. So I'm going to write that as negative dq. Again, that's a small amount of negative charge from the kind of positive conductor to the negative conductor. Which you can imagine then that the potential energy of the system, the two conductors, or the general, stop saying the two conductors, right, of the capacitor, this entire thing is what's called the capacitor, should increase. Each time he moves a charge over, again, to anchor our intuition with gravity, that's as if he were to carry a ball up a hill, which then gives that ball potential energy, the ball hill system some potential energy. So he moves a negative charge across the conductor, and we know that the change in potential energy is equal to the charge multiplied by the change in potential that that charge experiences. So again, this is just, we're drawing back from old definitions. And so now let me write this in the limit, in the calculus limit that we're working with. Since we're talking about kind of infinitesimally small amounts of charge moving across what could be a very large potential difference, right? The delta V could be very big, but we're moving tiny little amounts of charge. So really it's a dq, if we think of dq as a small little piece of charge. And then that's then associated with a small change in potential energy is equal to the small amount of charge that is moved times this delta V, which we said was just V sub c. Right, by moving that small negative charge across a potential, and let's be careful, I've already made a mistake, right? You might have realized I forgot a negative sign. So if it's moving an electron from over here to over here, what is the potential difference there? Remember, the potential difference is negative the integral of the electric field dotted with the path. So if you go from here to here, it looks like you're going from high to low potential. So this should be negative VC instead. You're going from high to low potential. Your ending potential is lower than your starting potential. So end minus start, that's a negative number in this case. You're going from high to low potential. So, and again, I could just be very explicit about where this came from. Let me move that over. Right, this is some small amount of charge multiplied by the ending potential minus the starting potential, which, as you can see, is negative what we are calling V sub c, or the voltage of the capacitor. So then, minus signs all cancel. It looks like the change in potential energy of the capacitor is Vc times dq. A positive number. Okay, good. That kind of jives with what we're thinking. I realize I'm not being very good at being consistent, because suddenly I've gone to lowercase q. This is what you get when you record at 9:22 p.m. So let's call this big DQ, big DQ, big DQ. So, but now let's also work in what we just wrote down for capacitance. We said that Q is equal to the capacitance times V. So if we're looking at this particular capacitor, then that seems like if I were to take the derivative of both sides, looks like dq would equal some constant times dv. And these differentials, essentially what I created a differential, which if you've done u substitutions with integrals, right, you've essentially done these but maybe not realize that's what you were doing. If differentials confuse you, you can always just imagine, take the derivative of both sides with respect to some other variable, like take the derivative with respect to time. And then both sides will have, it would then be kind of dq over dt equals c times dv over dt. And then you could just cancel out the dt's in the denominator, and then that gives you your differential. Don't worry if that didn't make sense. So the differential dq equals c times dv. So then it looks like, and technically v sub c. So then this looks like it's the change in potential energy is Vc times the capacitance times dVc, or that the change in potential energy is equal to some constant times V sub c times dVc. This is set up perfectly to do an integral. So then if I want to ask about what is the total amount of work that's being done, or the total energy that's stored by the demon moving all these electrons around, I could then integrate both sides. For the left-hand integral, we said that it's starting with 0 potential energy when there's no excess charge, and then it's going to build up to some general value of u that I want to then be able to read off. Similarly, the voltage, when the potential is 0, the potential difference is 0, and then that builds up to some value of V sub C. Whatever the potential difference that you've created across the capacitor. This also shows, if you look at this, this also shows that how much work does the demon have to do each time it moves another new electron over, that as it moves more and more electrons, there's a bigger potential difference that's created across the two conductors. This side gets bigger and bigger and bigger because it depends on V sub C. Every time it moves more electrons over, that potential difference grows and grows and grows. Then the demon has to kind of fight more against each, for each additional electron it moves over. So it makes sense that then this formula that we get at the end of the day, let me just kind of go down here to give it some space. The left-hand side just becomes U, and then you're integrating essentially a polynomial. This becomes C times 1/2 V squared. So then it looks like it's C over 2 VC squared. You can write it as 1/2 times 1/2 the capacitance times VC squared. Worth a highlight. Because this is then giving us essentially the energy stored in a capacitor. When you have a capacitor that has some capacitance, we still need to kind of figure out how we can figure out capacitance. When you have a capacitor that has a given capacitance, so C, the constant, is known, and you establish a particular potential difference across the capacitor, that stores energy. That creates an electric field between the two conductors. That electric field didn't come from nowhere. It came from this demon doing work. And so all that energy then becomes, that the demon did, or all that energy that was exerted by the demon, essentially becomes potential energy that is stored away in the electric field, or stored in this capacitor. And the total energy that it has is this kind of very simple formula. So this is a very good result. So, let's now actually calculate what the capacitance is for the most common type of capacitor, which is the parallel plate capacitor. So again, these are usually two thin sheets of aluminum foil with maybe something in between them. Let's do the case of, let's not have anything between them. Let's just have air or vacuum, but have two conducting plates that each of them have some area A, and they're separated by some small distance D, and then they are established either by a demon or something else that there's one that has some sort of positive charge and then one that has some sort of negative charge. So then as a result, there is an electric field that is established in between the two plates. Now let's actually calculate what the capacitance is. So the plates have each area A, and they're separated by some distance D, which is usually quite small. And that establishes an electric field. And we've talked about what the potential difference is across two plates. We've also talked about, since these plates are very, very close to one another, we've also talked that if there's an excess charge on the conductor, we worked out last time that the electric field is equal to the charge density divided by epsilon. That was the end of the previous video. Let's actually, and essentially now we're just going to combine all those results together. But I can, maybe I can just quickly sketch it out again. So there's the first we need to know the electric field, and then we need to know the potential difference across the plates, and then we will then use the formula that brings in capacitance to then figure out what the capacitance actually is. So let's do Gauss's law on the top plate. So you have the top plate, and we're going to do a Gaussian surface that encloses only the top plate. So this is a Gaussian surface that's going to enclose the top plate. And really, really what I'm doing is not really enclosing the entire plate, but I'm, let me actually redraw that. Because the top plate, if I zoom in, right, the top plate has some thickness. Some area A, some thickness. And I know the charges are all kind of residing on the surface, which I'll draw down there at the bottom. And then, because you could ask why the bottom and not the top. Well, no, remember there's that other plate down here where there's a bunch of negative charges. And the positive charges and the negative charges would like to be together. So you can imagine, probably with, not too much thought, that the positive charges are going to want to go to the bottom of the top plate because they want to be close to the negative charges, and the negative charges are going to want to come back, go up to the top. So I'm going to use a Gaussian surface that essentially includes that surface, but then it goes into the top plate like such. And why is that useful? Because I know the electric field right off the surface of the top plate is uniform and points down. So that when I evaluate the flux, and then the electric field is 0 inside the conductor, and then the flux is 0 through the sides of this surface as well. So it's really only kind of the bottom face of the Gaussian surface where there's any flux, any field lines piercing through. So by Gauss's law, if I evaluate the flux through that surface, that looks like it's then just going to be the electric field lines that are piercing the bottom face of this Gaussian surface, which then looks like, and since it's a uniform electric field, it's some value of the electric field E multiplied by the area of the plate A. And why is there no cosine factor? Well, the electric field points down, and remember that the normal vectors always point away from the surface so that they're parallel on the bottom face. So, so this is the total flux. And then by Gauss's law, that then is equal to the charge enclosed, which is just Q on the top plate, divided by epsilon naught. Again, if we assume for the plates that there's kind of a plus Q on top, and then negative Q on the bottom. Okay, not bad. So, let's set that aside. Or particularly we can say that the electric field in this case looks like it's going to be Q over A divided by epsilon naught. And then notice Q over A, charge over area, that's the charge density. I'm going to leave it as Q for right now. So, and then we also know that the potential across the capacitors is negative the integral of the electric field dotted with some path that I take. And we're going to start at the negative plate and end at the positive plate. So the path we're going to take, if I were to draw it out, I'll draw it out in blue. And maybe we start at some location at the bottom plate, and let's just go and walk straight up. Each little dr, we're going to just march straight up from the negative plate to the positive plate. Here I'm moving upward, my path is upward, but the electric field is pointing down. Those look like anti-parallel. So then this looks like it's going to be negative the integral of the magnitude of the electric field times dr times the cosine of the angle between them, which looks like it's 180 degrees, which is -1 from negative to positive. So then that looks like it's just the integral of the electric field magnitude times dr from negative to positive. The electric field we just argued is a constant. So then this looks like, again, it's just E times D, the separation between them, which is a result we've already seen. But again, it's always good to remind ourselves kind of where all this came from. That there was a reason we were doing it. All right, now let's put it all together. So I know there's a connection between the potential difference of the capacitor and the electric field. As you go from high to low, the delta V, right, goes down by E times D. But then the electric field we just said is Q over A. And then there's a D, and then there's an epsilon naught as well. So the electric field is Q over A divided by epsilon naught, rather, sorry. All that multiplied by D. Now let's actually use the capacitance result, that the Q is the capacitance times V. So then I'm going to write this as C times V. Then everything else, there's a D still, there's an A still, there's an epsilon naught. So then notice there's a V on both sides, so I can cancel that out. So then it looks like 1 equals the capacitance times D over A times epsilon naught. Or I can solve for the capacitance, and it looks like it's epsilon naught times the area A divided by D. And this is true only for parallel plates. Maybe I'll write that in blue to specify that there is a conditional. It's only true for parallel plates, though the other things I've highlighted, or rather the one thing I've highlighted, I should highlight the definition of capacitors, capacitance too. Where is it? There it is there. Let's highlight this. Right, the two things I've highlighted in green or yellow-green are generally true. This thing I've highlighted in blue is only true for parallel plates, right? This kind of brings in the geometry of the parallel plates. But you can see that it only depends on geometry, right? The area of the plate, the distance between the two plates. The epsilon naught, turns out, we'll look at this in problems, essentially is saying something about the material in between the plates. So if I were to fill it with some sort of gunk in between them, I would use a different value instead of epsilon naught, it turns out. So it's called filling the in-between with a dielectric, which then, unsurprisingly, is why epsilon naught is called, the dielectric constant. But note, it depends only on geometry. Let me commit that to words. Depends only on geometry. So that's also a nice result. And now one final thing, and then we'll be done. We've talked about, again, if I keep saying this idea that the energy is stored where, but it's stored in the electric field. Though as of now, it looks like when I talk about the total energy, or the energy stored in a capacitor, it seems like it depends on the capacitor and the potential difference across the capacitor. Now we know the potential difference connects to the electric field. But we can also write it more explicitly, which is kind of also a nice general result, in that we can define the energy density of the capacitor. And that's usually lowercase u, which again, an energy density is an energy per volume in this case. So I'm going to take the total energy of the capacitor, which we said was 1/2 capacitance V squared. And then I'm going to divide by the volume of the capacitor, which looks like that is just area times distance. If the area gives you the two dimensions, and then the thickness gives you the third dimension. So that's a volume. And then the nice thing that happens here is that essentially everything cancels. And so we have the 1/2. The capacitance we just derived and said it was epsilon naught times A all over D. The potential difference across the capacitor we said was the electric field times the separation D, and then that's all being squared. And this entire thing is divided by the volume A times D. And notice the areas cancel, all the D's cancel, and at the end of the day, the energy density ends up being 1/2 epsilon naught times the electric field squared. And the cool thing about this result is while we derived it using the parallel plates, you can actually derive it more generally, and this turns out to be kind of generally true. So I'll highlight it in green. That even if you didn't have parallel plates, but you had some different kind of capacitor, this result is still true. That the energy density, how much energy per volume of the capacitor is in that capacitor, you can see how directly it connects to the electric field. You establish a strong electric field, there's more energy kind of stored within the volume of that capacitor. This is a cool kind of general result. So, you may be asking at this point, okay, but how do we actually do this? I have two parallel plates. I want to establish a potential difference because I want to store energy between those two plates in the electric field, Dr. Lee. I don't actually have a daemon to do this. So, how do we actually do this? And we'll talk about that in more detail next time. But my answer to you really quickly would be to go to the store and buy a can of daemon. Before you unsubscribe and turn off the video, you can do this very easily. I have a box of daemon cans right here. And let me just open it up and show you one of them. That can actually help establish this sort of difference between the two sides of a capacitor. Essentially, that is the role of a battery in kind of driving this potential difference, which then allows the capacitor to charge up. So the next time we will start getting into kind of very simple circuit design and the roles of batteries and how batteries can be used to charge up capacitors and kind of what are equipotential surfaces within a circuit. All right.